SwayamPrabha. Digital India. Educated India.
Okay, so far we have been discussing essentially two-dimensional techniques, digital image correlation and photoelasticity, and there were differences in the two techniques. One was basically reflective technique. You look at light that is getting reflected off a sample that is deforming, and then you look at it and basically use that to evaluate strains and so on. The second photoelastic method was also two-dimensional, but it was transmissive, right. So we had a light source and then we had a polarizer, passed polarized light through the sample and then looked at how it changed, and using this transmitted information essentially we were able to reconstruct the stresses. So today we will move on to technique number 3, and unlike the other two, this is essentially a 3-dimensional technique. This is called what we call optical tomography. And this takes various forms, various guises. The most common one is X-ray, what is called X-ray CT. CT stands for computer tomography. And this has various applications ranging from industrial non-destructive testing to medical CT. Most of you have probably seen CT imaging done in a medical lab. The principles are essentially identical between all of them. There are some differences in the details, and we will look at them as we discuss the basic ideas that underlie this technique. Now before we get started, optical tomography has basically two aspects to it. If you recall our discussion about what happens when light waves come and interact with matter. Remember when we were discussing this idea about diffraction, I mentioned that there are electrons around these atoms, the nuclei, and because the incoming light wave is an electromagnetic wave, there is an electric field that is oscillating back and forth, and there is a magnetic field perpendicular to it. The electric field actually excites these electrons, and the electrons then start oscillating back and forth, and they start emitting their own electric fields, right, because oscillating charges will emit electric fields. So the electron has its own field that is generated. The sample comprising this entire set of electrons and oscillating things basically contributes its own contribution to the incoming field, and the final field that you see was, if you remember, a combination of what was coming in and what was generated because of the electrons. So remember we said when we started discussing the basis of diffraction, we said that if these two, for simplicity I will just call them E1 and E2, right. So E1 is the incoming and E2 is the one that is generated. If E1 and E2 are out of phase completely, so the phase difference is pi, then there is complete destructive interference between them, and this means that the resulting E, the final E will be 0. So the intensity of the field or the intensity of the light that you pick up will be 0. Now we also said that in the case of refraction, the actual phase difference, remember we call the delta, was close to pi by 2, which means that the wave was actually slowing down and this is the reason why the phase velocity in the medium was different from the phase velocity in free space, and so this is also why light rays bend when they come when they are incident at an angle to the interface. So this was responsible for slowing down, right. Now remember we also said that the actual value of delta is somewhere between pi by 2 and pi, usually for most materials, right. We also mentioned that there is a situation, there is a possibility that delta can be close to 2 pi, in which case the two waves will add up, and so that is what happens in a laser. We mentioned that I think in passing, but usually in most materials this is between pi by 2 and pi. Now in photoelasticity, the delta was sort of closer to pi by 2, So, the transmitted part was only dominated by the change in the speed, not the absorption. So, if you remember, this pi was because of absorption, complete absorption is delta equal to pi, and delta somewhere in between has a combination of both absorption and of change in wavelength, sorry, change in refractive index. So, in the photoelasticity case, we were usually not concerned with absorption so much, it was only change in the refractive index due to the stress system that was set up. But now in tomography, we are actually interested in the absorptivity part of this refractive index. So, if you were to take a course in light matter interaction or in the physics of laser lights or light sources and so on, the refractive index you will see is usually a complex number, and the imaginary part constitutes the absorptivity, and the real part refers to the change of speed. So, instead of going into those details, we just remember the fact that we are interested more in how stuff gets absorbed as light passes through the material. Let me just draw a simple example for you. So, let us say we have a cube, okay, and this is a solid cube. Let us say this cube is made out of steel, okay, some steel, mild steel, whatever, right. And behind this cube you have a screen, okay, and you pass light through this cube, okay. What you will see on the screen, you can do this experiment at home if you wish, is you will see a shadow of the cube, right. So, it is completely dark. So, in ideal case your light is everywhere. So, this is light or bright and this guy is dark. And the reason something appears dark is because there is no light falling on that, and so all the light that is passing from the source that is here to the screen is getting blocked out or getting absorbed rather, or even reflected. Nothing is getting transmitted through the block, right, which is why you see the shadow in the first place. Now, imagine if this block, if this light that you are passing were not actually, this is, you know, it is a light bulb, so you would imagine this is visible light, for instance, right. Now, imagine if you did the same thing with X-rays. So, you have same cube, I am going to draw it a little smaller, but you can assume it is the same cube, and I have a screen that is sitting behind it, and instead of now visible light, I am going to pass X-rays, okay. And if you do this, you will see that the X-rays, because X-rays get transmitted through metal, X-rays of a certain frequency for instance, you will see something that is reasonably hazy, but not quite black, okay. This is not fully black, but it is only partially, it is grey, let us say, right. This is all white or bright, but this is not fully black, and the reason it is not fully black is because the light that is coming in, part of it is of course reflected. So, if you look at the side view, if I look, let us put some axis here, let us call this Z, let us call this Y, and let us call this X. It does not matter, it is not a right hand coordinate system, does not matter. If we look along the x direction or the x axis, then, and if I just follow, let us say, some particular ray coming here, this is the incident ray, some part of it gets reflected, metals are reflective, they are reflective in the IR, they are reflective in the X-ray region also to varying degrees. The optical they are most reflective, which they are shiny as a result. So, some part of it is reflected from the surface, right, and the remaining is going through. Now, as this goes through, some part of it is constantly being absorbed by the metal as the light ray is passing through, okay. In the case of optical light, most of it is reflected, some of it goes through, and whatever goes through is very quickly absorbed very fast, right. So, this is X-ray, and if you had an optical light source, for example, let me maybe use a different color for this. If you had optical light, most of it is going to get reflected, some of it will get absorbed and it is done, nothing is transmitted, right. So, the result at the end is completely black, so there is no transmitted light, but in the case of X-rays there is something being transmitted, okay. So, you get some hazy grey image instead of complete black. Now, we can take this example a little bit further, one step further. Well, let us say we have not a cube, but a cube with a spherical hole inside, okay. So, the same metal cube, steel, whatever we had initially, it is the same cube, but now the cube has a small hole inside. Now, if you passed a visible light, optically visible light through this, which is the red rays, if you pass the red rays here, then you will get the same image that you had here. If you take a situation like this where you have a spherical hole inside the same metal piece, metal cube, and you pass visible light through it, then because we know the visible light is not going to penetrate through the cube long enough, it is not going to feel the presence of the hole firstly, but even if it did, it is not going to come out and tell you that it has felt the presence of the hole, okay. So, there is no way that the visible light will pick up the presence of the hole if you pass it, try to pass it through a metal piece like this. So, the resulting image that you see on the screen will be identical with the case without the hole, right. On the other hand, if you passed X-rays, remember we said that these X-rays are getting absorbed as they go through the material, and they also come out through the other end and they are transmitted out. So, you see a grey image. Now, because the hole implies that certain part of the metal, certain part of the substance is not really absorbing as much as certain other regions, you will actually see a higher intensity in the middle. So, you will see darkish grey here and a lighter grey here, and this of course will be white or bright or whatever the usual if the object was not there, okay. So, you can already see, and this effect is probably familiar to you if you have had a fracture and you have taken a bone X-ray, you can see the bones and you can see the tissues because exactly stuff like this happens, okay. In that case the bone is going to absorb more compared to the tissue and the flesh that is around, and so if you take a negative image the bone will appear brighter, that is the only difference, right, but the same idea applies. So, this concept is somewhat intuitive to us, but the whole point, the whole purpose of this part of our discussion is to be able to quantify this. How do you take an image like this and how do you reconstruct what is actually inside, right, that is what we are going to try and understand. To do that, let us now cook up another example. We will take two boxes or two cubes. The first cube is the same as our whole cube, right, with the spherical hole that looks like this, and we are going to pass X-rays in this direction. This was our Z direction, remember. I will put the coordinates again, this is Z, the other is X and Y, it does not matter which is which and the screen is basically the XY plane. Okay. So, the first sample we have is a metal cube with a spherical hole. The second sample is an identical looking cube. I will try to draw it as identical as possible, but even if it does not look the same, please assume that it is identical. But now instead of a spherical hole, it has inside it a cylindrical hole. Same outer dimensions and same material and so on. So, from outside it looks exactly the same. In one case is a spherical hole inside, in the other case there is a cylindrical hole. Okay. And you have the same screen that is sitting over here, and you are passing X-rays in the same direction along the Z axis. perpendicular to the xy plane. Okay. Now in these two cases what do you expect? Let us assume that this radius of the cylinder is r naught and the radius of the sphere is also r naught, okay. They are identical and the outer dimensions are also L. Cube, right. So all the edges are the same length, they are all equal in both cases, all 6 edges are the same. If you look at the image, as you can already guess, the image on the left and the image on the right will be identical, right. So the final image that you see, if you just looked at the screen, you will see the same image in both cases. You will see this lightish grey area, okay, and you will see lighter grey in the middle and you will see light or bright everywhere on the outside. Okay. From a shape point of view, the two images will look identical, but from an intensity point of view, the variation in intensity from this light grey to lighter grey or the medium grey to light grey if you like will be different for the sphere and different for the cylinder, okay. Because the light, if you look at a view from the x axis, I will draw a smaller version here, a smaller version here. In one case you have this, in the other case the cylinder will look like a rectangle if you look from the x axis, right. The first case, this light ray is getting absorbed more because it is passing through the metal more, so it will be darker, but this light ray that is going exactly on the diameter is getting absorbed much lesser and so it will appear somewhat lighter as it comes out, okay. So you will see dark, less dark and very less dark. So you will see a gradation, right. You already know then that there is some variation in the distance and typically from the single projection you can figure out that there is some gradation in the path length and so there is some absorption change as the material is traversed. In this case obviously the situation is very different, the path, the absorption here is the same as the absorption here. So you will see that the circle that you have finally will have more or less uniform intensity through the inside, okay. So a single X-ray shot can give you information about the shape that is inside, right. So that is the long and short of the example, is that a single X-ray image can give some, I am going to quantify, I am going to put this in quotes because we will quantify this soon, can give some idea about the interior geometry. Okay. But the problem is the following. So suppose and this by the way, this single X-ray shots are very common. If you go to, for example, an airport, you know, when you stand in the security line and you put your bag on the baggage tray, this is what is done. This is called radiography, X-ray radiography. It is also commonly done in non-destructive testing. So if you have a part that is being machined on a production line and you want to check if there are internal flaws or cracks and so on, or in a casting shop, in a foundry, if you want to see if there are internal pores or voids, things like that in the casting, then they are put on a conveyor and they are passed around, and then there is a system that will take an image in a single X-ray shot, and then you look at it and see if there are voids and so on. But it gives you a sort of a yes or no type of situation, right. You can, if there is a void like in the previous case, you will see that there is a void in the image, or there is a dark region or a light region in the image, but if it is not there, then it does not matter, right. So typically radiography, you get a single shot, and likewise with your bags on a conveyor, the airport security as well, you pass them, you take a single image and then you see, okay, something dangerous looking is inside, it is a gun, it is a knife, whatever, and then you know that it is a yes or a no, right. So this is a single image and it is mostly useful for pass fail type of situations. So even in the medical case, if you take an X-ray of your if you have a suspected fracture and you take an X-ray image, you can actually see a crack inside, and if the crack is there and you have a fracture, the crack is not there, okay, you do not have a fracture most likely, and so that is again a pass fail type of a situation. So a single image will suffice to tell you information about whether there is some internal structure or not, okay. But the problem is this does not, it turns out, does not uniquely determine the internal structure. Okay. A very simple way to look at this is basically to say, if the metals absorbance was very high, okay, let us say you are passing X-rays through lead or something which has very high absorbance, then the sphere, the gradation, the intensity gradation in the spherical cavity image, remember this was our screen, this was our image, and then you had this, the intensity gradation you will get here will be very similar to the intensity gradation you get here for the cylinder case, because this guy is so completely dark compared to this is completely bright in comparison, and likewise over here, and so the intensities will start matching. At that point you can't really distinguish whether one is a sphere, one is a cylinder, the signal is getting washed out and so on. So in these cases it becomes quite obvious that you can't use a single shot to determine the internal structure, okay. So as a result there was some discoveries that happened in the 70s, in fact this led to a Nobel Prize in the late 1970s, I do not remember the exact year, which uses this idea of doing what is called tomography, okay. And we have already seen this in a slightly different form when we spoke about photoelasticity. Remember we said that to determine the principal axis or the contours of the isoclinics you had to rotate the sample, but the sample was rotated in the plane perpendicular to the viewing direction. Now what you would do is you take your sample, in our case let us say the cube, you are passing light like this, you take the cube and you rotate it about this axis, okay. So you have this is equivalent to basically passing light in all directions and getting images in the corresponding directions, right. The equivalent thing to do is to rotate the cube in 360 degrees in a plane. So single axis of rotation, okay. So if you do this, there is a method of reconstruction that you can use. You take each of these projections, what are called projections, so each image, each single shot image is called a projection, and you stack them up. Again this is within quotes because it is not actually regular stacking, they are all in different directions, so you have to do something and then stack them up, and the next couple of sessions we will figure out exactly what to do before you stack, and you can reconstruct or recover the entire internal volume, okay. So if somebody really wanted to know the shape of your gun, if you were carrying a gun inside or a knife or a sharp object or a nail cutter or something inside your bag in the airport security, they would not be able to do that from a single image, but they would actually have to put your bag on a stage, rotate the stage and take a whole bunch of images typically covering 360 degrees, from which you should be able to reconstruct the entire shape, okay, and structure of internal structure too of the pseudo dangerous weapon you are carrying, okay. And this exactly is what is done in X-ray CT, or when you go for a CT scan this is exactly what is done. If you are lying down on a bed, you are passed through this ring, if you have had a CT scan done or if you have seen somebody who has gone through a CT scan, and there is a source and a detector is placed diametrically opposite from each other and they are basically rotated. So instead of you being rotated, which is not a very pleasant feeling, the detector and the source pair are rotated around you as the center of rotation. So it is essentially getting the same information, okay. So in the next session what we will do is we will set up some of the framework for how to do this recovery. So the whole thing we are going to build up to is to be able to do this type of recovery. Now there are state of the art techniques for doing reconstructions, it is an area that is fairly mature. There are lots of very robust algorithms for doing reconstruction of X-ray images. In fact, many of them work in real time these days. So, you can actually have real time high quality high fidelity CT reconstruction. But we will see the basic idea that underlies this reconstruction, and to do that we will have to discuss some ideas of Fourier transform, because that is one of the essential steps in inverting the actual signal that you get from a CT scan. And once we do that, we will look at something called the Fourier slice theorem, which helps us relate the data that you acquire to a Fourier transform of the actual density, and then using that we will discuss a few very simple, very elementary, easily implementable reconstruction techniques, and we will see how data can be recovered very easily using some simple steps. So, we will start with that in the next session.